Saxon Algebra 1, Lesson 99. You guys, it's our last two-digit lesson. Tomorrow we hit the big 100. But this is a great lesson because it's our third style of uniform motion problem, what I call DIRT problems, because the distance equals rate times time. We're going to recap the first two before we get into the third one. The first style is our Lord of the Rings style. Either two people are making the same trip, like Sam and Frodo are going to Mount Doom, or together they go to Mount Doom and then they go back again. Both of these fit the first model because the first distance is equal to the second distance. And that's true in this picture, right? The trips are exactly the same length. So we say that distance 1 equals distance 2. You can use letters as your subscripts if that helps you tell the story better. And then remembering that distance equals rate times time. We can blow this out a little bit, and instead of D, we write R times T, and then we use the same subscript so that we match all the right information. This then becomes the base equation that we use to fill in the 3 of the 4 blanks and solve for whatever's left. So that's the Lord of the Rings style. The second style is our Titanic. And in this one, we have things going bump in the night. This is the ship leaving England and hitting an iceberg that has chipped out of the Arctic Circle and floated down to the North Atlantic where it bumped into the ship. So two things starting at separate places but meeting in the middle. Oh, Grace wants in. Hang on. Come in, princess. Good girl. And the other style of story that works in this is here are Rose and Jack on the raft in the middle of the ocean after the Titanic has sunk. Here is Rose floating away to safety on the, I believe it was the Carpathian was the name of the other ship, and it should be going down, but here is poor Jack who dies, and he sinks to the bottom of the ocean floor. I'm very sorry to have to remind you of that sad truth, but his final trip is not a happy one. So sometimes things start together and then drift away from each other. Rose, in fact, went all the way back to New York. We could tell the story that way, couldn't we? And she lived her life in New York, let's say, and Jack's body was on the bottom of the ocean floor the whole time. In this case, the first distance plus the second distance add up to a total difference, a distance that I call K. John sometimes calls it N. I call it K. And again, we blow out the D's to make R1 T1 plus R2 T2 equals K. This is a base equation that we can then fill in the blanks and solve for missing pieces, right? We also sometimes get clock times instead of hours, and we have to convert our clock times. So we have a clock times chart. And I just want to remind you of how these look. We have a start time, and we have an ending time, and that we can use to calculate the number of hours. This is person 1 and person 2. Again, we often use letters instead of numbers, but these are the two different people usually in our story. There have been a few super tricky problems. Usually we get either the start or the end times. Sometimes we'll be given the hours and we have to figure out, or like we'll figure out the start time and we have to calculate the hours. We can get all different combinations of information for this chart. And some of the hardest problems are ones where we have to work backwards. We might get the hours and then figure out what time they started their trip or some crazy thing like that. So this is the third piece. This is our clock chart. John does not live in the reality of the clock chart. I made that up. So You won't see this in the solutions, but I think this is he expects you to just be able to organize and sort out all those times in your head. That's too hard. We make a chart of it. Okay, we're now ready for the third type. And you guys, I don't want to let you down, but my movie metaphor isn't as strong for this one. I'm pretty sure that Princess Bride, why am I not? Princess Bride. Yeah, I was trying to say Princess of the Bride. That's not right. That's Father of the Bride. I think I'm getting confused. Princess Bride has a lot of chasing, and that's what tile 3 is all about. This is about the chase. This is where maybe one person got a head start and the other person catches up. Or it might be about two people start at the same time, but one gets there faster than the other. In either case, there is a gap between the two distances that the people travel. This time we're going to use K to describe the gap, right? The distance that hasn't been traveled. And so the distances are unequal, but the gap balances them. So we can say, in this example, D1 plus K equals D2, right? This is the gap between them. And so again, if we blow it out, we see R1 T1 plus K equals R2 T2. And this works the same way. The distances are unequal, but K is the difference or the gap between them. And so we can add that into our equations, and that's how we'll balance. The Princess Bride, there's a lot of people chasing. There's a lot of head starts. There's a lot of situations where people start out from a chase scene and then one of them gets away. Sadly, I need to watch that movie over again so that I can remember details. But I'm pretty sure towards the beginning where Wesley is off being a mysterious pirate, and they're running away, and this is where they have the big sword fight up on top. I think there's this. I think that's it. Someone's going to have to help me fill in these details, or I'm going to have to watch it again. But this is where the sword fight is. I think that they catch up. But he came from farther away because he was busy being a pirate, right? So this is Wesley, and this is the bride and the dudes who have kidnapped her, right? And then this, I think, is in the scary part of the mountains after they roll down the hill. And I think this is where they get away in the forest. This is where Wesley and the princess are together, and they escape from the guys who are chasing them. Somebody's going to have to help me with that. We'll talk about it on our video chat. But I think that Princess Bride fits these scenarios. In any case, we can see these are the pictures. There's also a lot of Robin Hood tie-ins to this that I will talk to you about when we get into the problems. But in this case, we add the gap to the shorter trip, and that equals the longer trip. Okay, so let's practice a couple of these problems and see how they work. The hardest part is just recognizing this story format. Once you list out your variables and go from there, it's the same as always. Oh, I wanted to add to our notes, in this scenario, there's a third kind. I'm going to squeeze it in right here. It's where one person goes on a trip and then something changes and they keep going. D1, D2, K. There's a problem that involves somebody riding in a chariot and then the chariot breaking down or something and then getting out and walking the rest of the distance. That's this style of problem as well, okay? So sometimes the pictures look slightly different, but they still fit the basic equation. Okay, let's try an example. Now that I've confused you thoroughly. Do you feel confused thoroughly? I mean, I think I would. If I was listening to me try to describe this, I'd be like, what? Example 99.1. At 8 p.m., Achilles left camp and headed south at 20 kilometers per hour. All right, I'm ignoring the numbers and I'm just paying attention to the story. Achilles left camp and headed south. At 10 p.m., Patroclus headed south from the same camp. Okay, they're moving in the same direction. If Patroclus was 50 kilometers ahead by 3 a.m., what was his speed? Okay, so here's what's happening. They're leaving from the same camp and they're traveling in the same direction. So they're going like this. But by the end of our scenario, the second guy is further ahead. So that's how I know how to draw it. Let me read I'll skip the numbers. I'll just read the story part. Achilles left camp and headed south. Patroclus headed south from the same camp, and he was 50 kilometers ahead. Okay, so we know that there's a gap here, and we know that the gap equals 50. I'm going to write that down right away. Sometimes I just write the 50 right there. That helps me. This is the distance of Achilles. This is the distance of Patroclus. And I double check to make sure, yes, that's right. P is the guy who's ahead at the end. So I know that it's going to be like this, right? I can tell from the picture. This dude is longer, so this is the shorter dude, and he gets the gap with him. All right? Then I blow it out into RATA plus K equals RPTP. Good. I've already got my K listed, so let me list the others. RATA, RP, TP. And it starts out at 8 a.m., so I know, shoot, I'm going to need a chart for the clock stuff. And we've got starting time, ending time, and then the number of hours. And we've got Achilles, and we've got Patroclus, or whatever his name is. At 8 p.m., Achilles left camp. Okay. And he headed south at 20 kilometers per hour. That's a rate, so it's the rate of Achilles, 20. At 10 p.m., Patroclus headed south from the same camp. If Patroclus, it doesn't say how fast, so we don't know the rate of this dude. If Patroclus was 50 kilometers ahead, okay, that's the gap, at 3 a.m., so we know 3 a.m. is the ending time of our scenario, right? What was his speed? Okay, so that's what we're trying to find. So now we should be able to calculate the hours, right? Because this one's given us straightforward clock times. We can use it to find the hours. 8 p.m. to midnight is 4 hours, plus 3 more is 7. 10 p.m. to midnight is 2 hours, plus 3 more is 5. Okay, so the time of Achilles is 7, and the time of this dude is 5. All right, this was a nice, easy clock chart. That's, to me, the best way for them to work. And again, you don't have to make the chart if you can do this in your head, but it's too much to try and hold in your head. Write it down and organize it. It's much better. All right, now we've got all this filled in. We're ready to take our base equation and blow it out into buckets. And then plug in. All right, so I'm using these variables to guide me through my list. RA, 20. TA, 7. Plus K, 50. Equals RP, that's what we don't know, times TP, which is 5. Beautiful. Okay. Now I can summarize and get these numbers going. This I know is 140. I'm going to do that right away. Look, it's all numbers on the left. 140 plus plipty equals plun 90 equals 5 RP. And now we just divide by 5. And we get the rate of this dude equals what? Let's see. 5 into 100 is 20 times. And 5 into 90, okay, 5 into 50 is another 10 times, and then that still leaves us with 40. 5 times 8 is 40. So what I figured out is this is 38. If you just feel like you got hit by a truck with the way I did that, let's do it the regular way. 5 into 1, nova. 5 into 19, 3 times. Right? There it is again. Okay, so we get RP equals 38, and it's nice to put a rate, or to label your answer. There it is, 38 mph. Yay, oh, it's kilometers. So I fixed my thing. John sometimes writes kilometers per hour like that. Or you can write kph. I don't like the M in there. That was just me writing the wrong thing. These are the two options for writing kilometers per hour. I can live with either. Sometimes we'll use it this form when we need it for unit conversions, but this is fine too. So don't worry about that if John's writing it in the different form than you. If you got the 38, you're cooking with gas. All right, let's do another one. There's 3 in all in this lesson. Ready? Grace is ready. She just looked up at me all excited when I said that. She's wagging her tail. Rachel has a 25 kilometer head start on Charlene. Aha, this is one that looks like that. This girl there's a gap here because she has a head start. How long will it take Charlene to catch Rachel if Rachel travels at blah, 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 blah. So Charlene is chasing her, and we want to know when they're going to catch up. So it's like this. This is the distance of Rachel. This is the distance of Charlene. This is the gap. Cool, right? Let me read the story again so you can see how my picture matches the story. Rachel has a head start on Charlene. There it is. That's the head start. How long will it take Charlene to catch her? And there's the picture showing that they catch up in the end. Okay, the distance of Rachel plus her head start equals the distance of Charlene. And now we blow it out. RRTR plus K equals RCTC. Cool, right? All right, let's list our variables. RR, TR, K, RC, TC. Ideally, I like to put these in the same order that they appear here, so when I go to fill them in, it'll be really easy. But it's not the end of the world if you don't. I'm just always looking for ways to make it easier. You know what I'm saying? All right, ready? Rachel has a 15 kilometer head start. Okay, head start means this, right? And so that means K equals 15. How long will it take Charlene to catch up if Rachel travels at 70 kilometers, that's the rate of Rachel, and Charlene travels at 100 kilometers per hour? Okay, there are no times anywhere in here, and the story isn't explicit, but what we're supposed to take away is that they're both running for the same time. This girl has a head start, but we're supposed to assume that like somebody yells bang and they both run and this girl catches up. That's kind of subtle, but we're supposed to assume that the time is the same for both of them, okay? When we establish that the times are the same, what I like to do is just change it to a plain T. We don't need time of Rachel, time of Charlene. It's the same, so we'll just have time. That's gonna make things easier when we go here. So now I'm gonna set up my buckets. Rate of Rachel, 70. Time of Rachel, oh, we're just using a plain T, plus 15. Rate of Charlene, 100. Time of Charlene, oh, also just a plain T. Beautiful. We clean this up. 70T plus 15 equals 100T. Swim the T fish that away. Goodbye. 15 equals 30T. Thank you, John, for the easy math. Be careful, we're used to having these turn into whole numbers. This is so easy, it's hard. T equals 1/2 of an hour. That's how long it's gonna take Charlene to catch up with Rachel. That head start burned itself out after just a half an hour. I wonder why Charlene is so much faster than Rachel. It doesn't say if they're, I mean, I can't believe they're running 70 kilometers an hour would be quite a clip. So they must be driving. I'm gonna say dune buggies because I think they're really hauling. And if they were driving on the expressway, this wouldn't be that fast because 100 kilometers is like 60 miles an hour. So it's fast, but it's nothing interesting. It doesn't make an interesting story. It's just like moderate expressway speed. So I'm gonna have them in dune buggies because I like that story better. Okay, now for the third problem that has a little bit of a trick to it, which is why I'm glad we're doing it together so you don't encounter this in the wilds of your homework and go, what in the world? Harry and Janet jog around a circular track that is 210 meters long. So immediately our brains go, what? Our pictures all have straight lines and they're jogging around a circular track. How are we gonna make sense of this? Okay, hang on. I agree, that's a good problem. Janet's rate is blah, blah, blah. Harry's rate is blah, blah, blah. In how many minutes will Janet be a full lap ahead? So they're going around in circles. How are we possibly supposed to figure this out? What we do is we change their circular track into a straight line. What? How do you do that? You just draw it, right? Which one's running more? Janet is going to be ahead. Okay? So they're running around and around, but if we take their track and untangle it and make a series of long tracks, this is what it looks like, right? Maybe that much of it is one circle, and this is 2 circles, right? And then this is 3 circles. I'm just pretending. I didn't measure that out exactly. But that's how we can see their round laps as a straight line. This is the first lap. That's the second lap. 1, 2, 3. That was just my guess. I'm not suggesting that we can use this to figure out the numbers, but I'm saying we can just imagine these circular trips as straight lines being added to each other. Take a second and wrap your brain around that. That just because they're running on a circular track doesn't mean we have to envision their progress as a circle. We can basically take that circle and open it up. Obviously, the length of this circle is a lot shorter than what I've drawn here, but you get the idea. We can imagine this not as a circular trip, but as a straight line, a series of straight lines, right? Each one of these as long as the track is. The track is 210 meters long. Okay, we don't know what to do with that just yet. But let me write this. The distance, this is the distance of Harry. He's the slower one. This is the distance of Janet. He's the one that's going to be ahead in the end. Okay, the track is 210 meters long. I don't know what to do with that yet, but I'm going to figure this out first. The distance of Harry plus the gap equals the distance of Janet. So now we blow it out. RHTH plus K equals RJ TJ. I always want to make it a DJ, but we already did that. Okay, this is our thing. I'm going to squish my letters in here. RH, TH. I'm going to slide this up a little so it's easier for you to see. K, RJ, TJ. Okay. Let's get the other numbers. Janet's rate is 230 meters per minute. The rate of Janet is 230. While Harry's rate is only 200 meters per minute. In how many minutes will Janet be a full lap ahead? Okay, we don't know the time. So once again, we're going to just let both of the times be t. Now, we don't have the length of the gap, but we know that the gap is 1 full lap ahead, and we know that the track is 210 meters long. So this distance, this gap, is 1 lap. And we know that the track is 210 meters long. So 1 lap equals 210 meters. So that is what we use for our value for K right here. Make sense? That's a T there. That confused me. All right, again, our times are the same, so we just use T. Notice that I'm not paying any attention worrying about the units, right? They're changing from kilometers to miles and from hours to minutes. That's okay. John does not cause us drama by mixing those up within the problem. In more advanced classes, he might quote one person's time in minutes and another person's in hours, and we would have to fix that. He does not play those games with us. We can just know that if it's a time, it matches to the other times. We don't have to worry. Okay, so now we've got this all straightened out. Let's set up our buckets and start filling in. Rate of Harry, 200. Time of Harry, just plain T. Gap, 210. Rate of Janet, I don't think I've ever heard that story before, that name before. But I'll tell you what, I've done these problems so many times. You guys, I've literally taught this class. I am quite sure I've taught Algebra 1 every single year since 2002? 2002, before you were born. I have taught this class every year. So Harry and Janet have been trying to run around this dang track for a long time, and they're like old friends to me that I come back to. Okay, ready? So now we have $200T. Sorry, I got distracted looking at something in the book. Plus 210 equals 230T. We're just doing basic algebra now. Let's swim the T fish over to leave this plain number by himself. This one's a little bit crowded because I'm squishing into this space here. 210 equals 30T. We divide by 30. This cancels, and we get the time equals 7 minutes. So Janet is going to destroy Harry on this track in a mere 7 minutes. I mean, maybe Harry is a baby and he is crawling, and maybe Janet is like a world-class athlete who is sprinting. So 7 minutes actually would make me very proud of the baby. We just don't know. Maybe they're animals, right? Maybe Harry is a turtle and Janet is a hare. Oh, that would be interesting. I spend a fair amount of time, you guys, just wondering what the heck is going on with these problems. It's a little something I do to amuse myself because story problems are hard. And in order to keep ourselves from losing our minds, we have to find a way to enjoy them. I personally take a certain amount of interest in building ridiculous stories and just thinking about them in overthinking ways. As long as I don't overthink my math, I can overthink the problem, the story all day long. All right, that's the end of lesson 99. Let's cross it off. I am done. Thank you for your rapt attention. Goodbye.